All right. Share my screen. Nice. I already did. Oh, where we go with this? Seems fine. I'll minimize it maybe. All right, guys, we'll get started in a few minutes. I'm just finishing setup here. Cool. All right, everybody. So a few announcements and then we'll get started. First of all, it's so nice to see so many people in the same room again. I know things are ramping up with academics. We're starting to get into the midterms and the final season. So hopefully this meeting will be valuable to you guys because we want to respect your time, obviously, because everyone has things going on and studying. We have a very special guest. So I'd like to introduce him, Josh. Why don't you come and talk to the students a little bit about your initiative?
Hey guys. I just gotta pause.
Yeah, you want to start?
So I'll be brief. I actually did my undergrad here 12 years ago. I did math and economics. This was before machine learning was a thing. Well, it's kind of a thing, but they called it something different. I did a PhD in statistics at UCLA, finished in 2015. I've been working in data science since about 2012, kind of worked while I was a grad student. So I've been in the industry about 10 years now, and I've gone from doing a bunch of like math, heavy modeling stuff to mostly building machine learning systems in the last couple of years. So what I got connected with you guys is I'm friends with Kristen Jaski, who's your sponsor or
She's our
advisor. I'm close with her brother. We actually spent some time in undergrad, grad school together. And a thing that I'm working on currently, so my day job, I work at a biotech company remote. I live here in Phoenix. Companies sort of distributed throughout the country. But a side project I'm working on is trying to scrape public data, public records, satellite images, various aspects of properties to do some projects on real estate. So there's a small group of us that are interested in a variety of things from lead generation to predicting whether or not solar panels will fit on roofs. So we're going to see if I can advise you guys on some machine learning projects and see if some of you might be interested in doing some work, either through some kind of internship program or something more informal, just to get you guys some real world experience and to get me some extra hands to do heavy lifting in terms of web scraping, data processing, things like that. So I'll be sitting right there. I may ask some questions, and then maybe we can leave some time. You guys are welcome to ask me anything you want about career stuff, jobs, projects, ideas. If you need Calc 2 tutoring help, I can also do that for a couple of minutes, although it's been a while. So I'll be here. Feel free to bother me. I'll hang out for a while.
All right. Thanks so much, Josh. So the topic we're going to be talking about today is probably one of the most interesting ones. So to get you guys excited about it, we have pizza. So why don't you guys go get a few slices and then we'll get started. Oh, how many do we have in the Zoom? Do you want to go up to the pizza, make sure everything is really good? 7 people on the Zoom. Solid. Nice. Unfortunately, we don't have plates, so we just have the students get napkins. It's not like we can't afford it, but it's just something that we always forget about. So Walmart, I guess, I don't know. These are the problems we're facing as an organization. Well, Tal has a car and we have a credit card, so we're good. Yeah.
I picked them up at 5:15 in the traffic, but they gave me a hour to get back.
Really?
Also, like a little bit of forethought and planning, like
There's actually a lot of like regulation in place for purchasing at ASU. So much, you'd be surprised. Like for us to get approval to buy pizzas at general body meetings, it was a nightmare. Just get a bank account. Surprising. But yeah. Grateful we have it. No, yeah, I mean it is. All the regulations go all the way up to the state. So it's not really in our control, unfortunately. So in the chat, make sure to let me know if there are any questions. Sounds good. Yeah, just let me know if there are any questions. If you want, send a general message in the chat. Okay, if you have any questions, just let us know. All right, guys, we'll get started in a few minutes. So try to make your way towards sitting with the pizza and we'll start getting into this awesome topic. Hey, Rashid, Karthik, if you guys want to grab a slice, go ahead. You sure? Did you guys eat? Rashid, grab a slice, bro. There's enough. We have 10 pies. Come on, man. Come on. Go get one. You sure? Okay. All right. Good. Hungry House is all right. If we have a better budget, one day we'll get like top tier pizza. But right now. Yeah. All right, guys. I'm gonna get started. So the topic that we're going to be talking about today is convolutional neural networks. So I don't know how many of you guys were here for Dr. Jassky's talk about neural networks. Could you guys raise your hand for those of you that were here for Dr. Jassky's talk? Okay, so I'll spend a little bit of time talking about neural networks. But generally, I'm going to kind of jump into the image processing application of CNNs. And then I'll show you guys a little cool demo, which is kind of like the whole MO of this meeting. Related to sign language. So why don't we get started? Everyone up there good? It looks like there's a war over the pizza. All right. So one thing to talk about in this specific presentation is that this presentation is not exhaustive, meaning CV specifically is a world that is constantly being researched, and there's a lot of things that I'm either going to omit because they're too complicated or things that I'm going to ignore just for the sake of introducing you to this topic. I think this is one of the most fun topics to explore because the direct application is very easy to see, processing images, object detection. It's possibly one of the topics that's most demoed, or one of the applications that's most demoed. So just have that in mind, and I'll send out a list of resources that I use to build this presentation and some resources you might want to use to explore after we kind of talk about this. So the first thing is, let's talk a little bit about what vanilla neural networks do. So they take some set of inputs and map them to an output or a set of outputs. The limitations of a vanilla neural network on images is if we're just taking all the pixels in an image and feeding it to a neural network, that kind of limits us from the information or the features that we can extract, because we're really just viewing individual pixels. we can't really get too much information from individual pixels, and we can't really understand what the neural network is looking at when it's just taking individual pixels as inputs. One great example of an exploit that exists with vanilla neural networks for image processing problems is the MNIST dataset. Probably all of you guys have seen it. It's that dataset with the little handwritten digits. It's like the hello world of ML. And an exploit with that is if you use a regular neural network to process MNIST data, there's a specific pixel in the data set, in the images, that if the neural network recognizes that that pixel is relevant to the prediction, it will be able to predict with almost 98% accuracy what the output will be, and it can ignore almost every other pixel in the image. And so the problem with these regular neural networks is complex images are really hard to deal with, and it's really hard to map that complexity when you're just taking individual pixels as inputs. So recall what this looks like. We have some digit 9. It's a 28 by 28 image. 28 times 28 is 784. So we have 784 inputs that's processed. And then ultimately we have this output layer that determines that the image that the neural network is looking at is a 9. And convolutional neural networks at the end function very similarly, but in the middle and the hidden layers and in the input function very differently. And that's what makes them so powerful. And we're going to talk about all of that very shortly. All right. So what's more widely used for images is convolutional neural networks. And let's talk about why. So the concepts that we're going to be talking about today, and if you guys want to take notes, feel free to, is going to be these 5 topics: filtering, convolution, pooling, dense layers, and then we're going to talk about this cool demo and a GitHub repository you guys can build off of if you want to explore a little bit more about CNNs. So one thing to remember is that when we're processing images, images are just a set of pixel values. So you can see this flickering image of this 8, but really the way the computer is viewing this 8 is just a matrix of pixels. And when we're talking about black and white images, we can say that the image is one-dimensional. And when we talk about red, green, and blue images, images that have colors that range between those 3 colors, those are 3-dimensional because there's a layer of pixels that accounts for the amount of redness in each pixel, the amount of greenness in each pixel, the amount of blueness in each pixel. So remember that when we process an image, ultimately, an image is a matrix of pixel values. Okay, so now filters. So convolution, the whole idea of convolution is based off of this idea of filters. And the purpose of a filter is to extract important information or important features from an image. So I'm going to show you guys a little animation to show you how these filters work. So you can get a little intuition about how filters applied onto images can extract some features. And there are going to be a lot of animations here. So if you want me to stop or explain something, feel free to just ask for me to stop. Okay. So as you can see, this filter is being applied onto the matrix of pixel values. And this is a very small, low dimensional example where it's a 5 by 5 image and a 3 by 3 filter. So the way convolution works is that we have this orange matrix we saw on the previous slide. And we have our image matrix, and we're moving this filter one by one, like pixel by pixel, for every position, okay, to compute the element-wise multiplication between the 2 matrices, add the outputs of that, and create a convolved feature, which means we're taking this filter, running it across our image, and producing some output. Now, what is the output relative to the original image? The output is telling us some of the key features that the filter found in the image. Now, let's think really quick. That filter is not the only type of filter we use, meaning the values in the filter, the size of the filter, and the signs of the values in the filter can all be different, which means the values in that 3x3 matrix, as we change them, can tell us different things about the image as we create this convolved feature map. So the way convolution works, as we just reviewed, is we have an image, we apply a filter, and don't interpret this math literally, but we apply a filter, and our result is some feature map. And as we discussed, different filters or different values in the filter matrix will yield different features that are extracted from the image. And so this process is called convolution. Now I want to give you guys a little bit of a visualization. So we have this image, looks like a rabbit. And based off of the different values and signs of the filters, we get different functions of our convolution. So you see the first one is an identity filter. It means it's not doing anything to the image. And then we have these different filters that are doing different types of edge detection. We can sharpen the image, we can blur the image. And there are researchers that focus their entire work on just what is the most efficient way to blur and unblur an image. It's an entire field in itself. Data augmentation is super important, as you'll see in the training process, and we'll talk a little bit about that later. But you can see how powerful filters can be. As you change individual values, it will change the feature maps or the outputs that you get as you apply those filters onto the images. Another cool example, I love these animations. This is another one. We have some red filter that goes over the image and produces some output. And then we have this green filter that goes over the image and produces some output. And the outputs are different. And these outputs tell us different things about the images. Now, why would someone want to do something like this? The CNN learns the values of the filters on its own during training. And the more features that get extracted by using those filters, the better the model will be when it sees new images. So the goal of these filters is to extract important features from images that define the image's complexity, and then use that and look at new images and see if those features match, if they deviate. So that becomes very useful in object detection, facial recognition, problems like that. That becomes very, very useful. So we're back to this MNIST example. In a single convolutional layer in a neural network, we can have multiple filters, which means we can filter an image a bunch of different ways and extract different information. Just look with me here. For example, what information do we get from this image versus what information do we get from this image? We're getting different pieces of information. Maybe that the oval part of the 9 is highlighted here. Maybe that the long end of the 9 is highlighted here. And so when we identify these unifying features that exist in images, we can say, well, a 9 has this oval piece, and it has this long piece, and it has this little underside piece. This new image must be a 9. That's one potential application of feature maps. It's not that easy, and it's not exactly how CNNs work, but that's a great way to visualize how a CNN might use these. So I'd like to define a few kind of features of a feature map, like a few definitions. So depth is something that it's a definition corresponds to the number of filters we use for a single layer of convolution. So if we had a depth of 3, we'd be using 3 different filters on a singular image. And you can think of those different filterized images being stacked like pancakes, for example. And then you remember when we had that orange matrix that was sliding across the image? So stride refers to when the matrix itself slides over, how many pixels is it sliding over? And that becomes important because if you want to, for example, only look at the corners of an image and you know the dimensions of the image, you can set your stride to go from one corner to the next without looking at anything in between. So stride becomes really important when you're trying to identify certain locations of an image and what those locations tell you about the ultimate output. And then zero padding is a technique. It's a little complex, but it's basically the use of a zero around the border of an input matrix, so we can apply our filter to bordering elements in the image. And I encourage you to do research about how these three factors affects the performance of the model, but the one we're going to talk about most is probably depth and stride. Okay, so up until now, what we've been able to talk about is we're taking an input image, we're applying a filter or some set of filters onto that image, and we get this convolutional layer, where we get these outputs, as we call them, feature maps, right? Because we're taking these filters, extracting features, and we're constructing feature maps. One technique that's used to extract some more key information from the images is using something called ReLU. And ReLU stands for rectified linear, I forgot the U. Unit, rectified linear unit. And what this does is it takes the value of a pixel, everything that's negative, and it puts it to 0. And any value that's above 0, we don't really care about, but all the non-negative values we don't care about, all the negative values we want to set to 0. And this becomes important because ReLU allows us to refine what we're looking at in certain feature maps. And a lot of the techniques that we're going to talk about help us refine feature maps, help us identify more specific features, more specific lines in an image. Getting the most important information from an image is crucial because we're trying to make this computation as fast as possible so that we can detect images and identify key features in an image really, really quickly. So when you're building convolutional neural networks, you usually have stacks of layers between convolution and pooling layers. So when we talk about fast computation, pooling is something that aids that. Pooling allows us to reduce the dimensionality of our feature maps while retaining the most important features. And the way this works is really simple. For max pooling, let's look at this green section in the image, and we're going to have images that are probably way larger, but this is an oversimplification so we can kind of understand how it works. We have these 4 values, 29, 15, 0, and 100. Max pooling is taking a value in a set of values and taking the maximum value and reducing dimensions, or reducing the dimensionality. So you can see in the red region, 28, 184, 70, 38, we're taking the largest value, 184. We're taking the largest value here, 12, 12, and 12. 12 is the largest value, and 45 is the largest value. Average pooling is taking the sum of all the values in some region and averaging them out. And max pooling has been identified to be more effective, and there are many ways of there are many different ways of pooling. There's attentive pooling, average pooling, max pooling, but max pooling is probably the one that's used most traditionally. So I'd like to visualize this entire process because we talked about features so much. So this may seem like very scatterbrained and kind of complex, but I want to break it down for you. As we do more layers of convolution, the model can identify more specific things about the image it's looking at. So in the beginning layers of convolution, we're going to identify very high, very high zoomed out type features that don't tell us too much about the specific things about the images. So like we would refer that as a low level feature, something that doesn't tell us too much about the image. Maybe generalized lines or structure. A mid-level feature gets more specific, and then a high-level feature gets even more specific. You can see that in high-level features, the model is identifying the wheels. If you can see in the top left here, you can see that wheels are being identified. And I know it's a little blurry. You can also see that the grille of the car is being identified right over here. So this is really cool. Kind of proves to us that a model can take an image and strip it down to its key features and ultimately identify what defines the image. And this becomes so powerful because, for example, in a problem like facial recognition, when we strip down someone's face to the key features of the face, we can identify what that corresponds to or what that is closest to. So what does a full architecture of a CNN look like? So we start with some input image, and we're iteratively doing convolution ReLU pooling. And then we get to these feature maps, these really, really specific feature maps that we just talked about. And what we do with the really, really specific feature maps is we flatten them into individual values. And we do what we did with the vanilla neural network. Remember, we had that MNIST digit and we fed the individual pixels into the neural network. Once we extract the really high level features, we take the same approach. But what's different here is that in the original vanilla neural network model, we didn't have all the really specific information. We just had a very generalized image with a lot of background noise and stuff that doesn't matter to us. Here, these features tell us a lot about the image, so we can feel confident that they'll influence our prediction. So we feed those high-level features into a dense neural network, and we ultimately have an output, and the output is defined by how many classes we train the model on, and usually softmax activation function is best, and we will get an output prediction. I'd like to spend some time answering questions if anyone has any questions, because I just kind of dropped the bomb on you guys. So if you have any questions, I'd love to answer those.
So for the convolution filter, so how is there a hyperparameter for choosing the values for that?
Yes, so the learned aspect of the CNN is learning the features that define, or learning the filter values that define the most important features. So that is what's being learned. The filters is what is being learned.
Okay. So if there's a horizontal filter that filters all the horizontal patterns now. So for each image, there's a different filter to extract the horizontal lines.
So are you saying are filters specific to individual pictures?
Yeah.
So just like in a regular neural network where you had different training examples, the model was able to generalize over time and create a set of weights and biases that fit a general data set. The same thing is true here, just with filter optimization rather than just weight and bias optimization. Does that kind of answer your question? Okay. Any other questions? Yeah.
So every step in this process is represented by a matrix, right?
Yeah, most of the operations here are between matrices. Yeah.
And does that change in the flattening process?
Yeah. So once you flatten a matrix, you flatten it into just an array.
Oh, okay.
Just an array of values that's fed into the neural network.
Are these tensors?
Yeah. So for images, it depends what type of images you're working with. In a specific demo that we're talking about, if it's a black and white image, then it's not a tensor. But if it's a red, green, and blue image, then it is a tensor because then it's three-dimensional. A tensor is just an n-dimensional matrix, right? So yes, it would be a tensor if you were working with colored images, but in the specific case that I'm talking about, we're working with black and white images. Yeah, that's a great point.
Because in the previous example, we showed that there's like many feature maps that are generated.
Yeah.
When you flatten them all at once, or you do them individually, and they all get like a rerealize on a group.
So the most important feature maps that the model identifies are flattened and then fed into the neural network. Let me show you guys a visualization that enlightens that for you. I'll answer your question first.
Outside of just adding more layers, more training time, and what kind of feature engineering do you do to improve performance?
So to my knowledge, a lot about constructing model architecture for CNNs is really just working with them for a long period of time. But something that you can do in the training process before the images are even fed into the into the convolutional neural network is you can take your training data and duplicate it and transform it and blur it. So to generate more data for the model to be more generalizable on new data. So for example, if you had a picture of a dog what you could do is flip it and transform it in space. So it looks like a different image to the model, but you and I know that it's the same image, but it becomes another data point for the model to train on. In terms of architecture engineering and feature engineering, I don't know too much about that. You would have to do some extra research about that.
So, excuse me, because I want more like.
Sure.
I was just wondering, so with these models, is there like a way to know your optimal number of feature maps, or is it more so just more data, better data?
So like a optimal depth,
Yeah.
you're saying?
This optimal like value to like optimizing performance based on feature map.
Okay, so obviously with any machine learning model, you can, for specific classification problems, you can measure accuracy and you can do F1 scores and you can do confusion matrices and all of that. But in terms of depth, that is specific to the problem really, because simple problems with 28 by 28 images, you're not going to need a very, a varied amount of filters used. But in a very, very complex image problem, you might need a set of 20 or 30 filters, and some image problems require three-dimensional convolution, which is a whole another world in itself. But again, stuff like depth, specific variables like that is really specific to the problem that you're attacking. No, CNNs can be used for a variety of different problems. I've seen them used in NLP. I'm not exactly sure how they work in regards to NLP. Yeah, I actually don't know what it means in the NLP context. I think we have a PhD student who's in NLP. Maybe you could enlighten us a little bit about how convolution is used in NLP.
Well, like they use it in like summarization, text summarization, to try to get to the important parts of the paragraph. So convolution would exclude things that are important. Also, there's graph convolution, where they go into like a graph and they pick the edges that are more important, the same kind of way they're using images.
But graph is again an image.
So what?
Graph is again an image.
Graph?
Yeah.
Well, yeah, I guess graph convolution is a type of image convolution.
That's my question. It's a graph convolution similar to an image.
Yeah, it's the same thing where it's like pick out the important things or the relevant pieces. Because that's really what this is doing. Convolution captures various image, like the changing parts of the image. That's what it's trying to capture.
So in the case of NLP, how is the filter design? Is it similar to how it is in images or it's completely different?
Well, I mean, it's all numbers. Like he was saying earlier, everything's a number, right? So if you can get a word into a numeric representation, you can just use the same process.
Just like you do tokenization in NLP and look at word embeddings and compare distances between word embeddings, you can do very similar processes. Yeah. Any other questions? Okay. So if that's the case, I'd like to show you guys a really cool but scrappy demo that I threw together. And this is an architecture that I made on my own. A lot of times CNNs are pre-trained on a huge data set of images. If any of you guys were at the hackathon, actually, there was a team that took speech and converted it into text and then fed that into a generative model that made new images. The same kind of concept, we're training models on huge amounts of data. CNNs require a huge amount of data to classify very specific images. So this demo is just a demonstration of what you can do with an architecture that you can build on your own. I'll show you guys a video and then I'll send you guys the GitHub link so you can tinker a little bit with that. Excuse my very serious face in this, by the way. So I'll give you a little preface to this. I was trying to build a sign language detection model, and I was training it on 3 different gestures. So no, I love you, and hello. And this is like a very basic demo. And if you want to roast me afterwards about how scrappy this is, feel free. I'll be here for a while, so I'll just press play. So it's identifying that I'm wagging my finger and saying no, and then it's identifying that I love you. The bounding box is not moving. The bounding box is fixed. and then it identifies that I say hello. And you can see that it's moving back and forth between I love you and hello. And the certainty value is definitely relatively high. What's cool about this demo specifically is I wrote a piece of code for you guys to actually build your own training data set. So if you want to do this on your own with whatever gestures you want to create or whatever problem you want to attack, I built a repository, very simple, that I'll put in the Discord, and you guys can definitely take a look at that. The architecture is obviously up for you to change. I mean, this is not the best architecture. It's like 2 convolutional layers, 32 neurons, and 3 output neurons in the output layer. But feel free to take a look at that GitHub, build on top of it, fork it, and send what you guys come up with in the Discord. We'd love to take a look. We're here for questions. Josh is definitely here to chill with you guys for a few minutes. If you have any hackathon related questions, project related questions, we're here. And if you just like to chill out and talk about ideas, we're also here for that. So thank you guys so much for coming. We really appreciate it. I'll send that GitHub link so you guys can take a look, and have a great week. All right.
Your mic muted? Or Zoom off, I guess.
All right, guys, I just sent that GitHub link so you can take a look. You can feel free to roast my profile picture. I took it in 11th grade, so. When am I updating it? I'll update it when I feel like I need a new profile picture. What? Discord, yeah. Is anyone not on the Discord, by the way? Great, awesome. Yeah, there we go. When's the last time you updated your profile photo?
2018.
2018. I believe that's
That was
4
like
years
a
ago.
conscious effort, because I was like, God.
All right, I can respect that. Yeah, that repository should be public, so feel free to take a look. And if you want to fork and build on top of it, go for it.
How did your classifier do?
So training accuracy was like 92%, and validation accuracy was like 83%.
Was it on the static image? Is it?
So what I did was in OpenCV, I restricted the view of the model to that static bounding box. And then I just put my hand in the bounding box, took that, reduced the dimensionality and put it into the model, and added a small delay. And then I just saw the output of the model.
How many examples?
So I sat in my dorm room yesterday morning, just holding my hand like this for like 20 minutes. I had like probably like 1,800 images.
Oh, okay.
I mean, it's not bad for a pre-built,
That's not bad at all.
for a from scratch
I
architecture.
mean, like, I remember when people applied, they used like gradients, they used that extra boost basically on NDisk.
Yeah.
And got like 90%, and it was like, yay!
Yeah. Yeah, we did a MNIST project here a while back, and people really loved it. I think it's one of the best data sets.
Yeah, and it's actually like the post office uses it.
Really?
Yeah, so I think there was an earlier version that did like handwriting recognition for like detecting addresses.
No way.
Like I'm pretty sure I'm not sure which version, but I know the post office uses some version of handwriting recognition to get numbers for addresses.
That's
So
awesome.
it's like shit actually gets used.
I didn't know that.
What's up, man?
Nice to meet you. I'm John.
Nice to meet you. I'm Noam. Yeah.
Good presentation.
Oh.
Assuming you're a student here.
Yeah.
That was really good.
Thank you so much.
I had a quick question about AIs. I'm assuming you would be the one that talked